Welcome to an introduction to stoichiometry. So our goals for today explain that coefficients in a balanced equation can be interpreted in terms of moles and can be used to build something called the mole ratio, and then use that mole ratio to do some conversions around a balanced equation. So stoichiometry really ties together two things that we have been studying recently. So stoichiometry is defined as the calculation of quantities in chemical reactions. So when you think of chemical reactions, of course, you think of equations. And another word for quantities is amounts. And the way we measure amounts in chemistry is with the mole. So all stoichiometry does is tie together equations and the mole. What could be better? So let's think about a balanced equation. We've been balancing equations recently, and if we look at this equation, right, the way we've been interpreting it is in terms of particles. So for example, that 3H2 represents 3 molecules of H2, and we combine that with 1 molecule of N2, and that will produce 2 molecules of ammonia, NH3. But right, this is a proportional relationship, and if we kind of scaled everything up, if we said, well, what if I just multiply all those numbers of particles by 6.02 times 10 to the 23rd, right? Then we could also interpret the balanced equation in terms of moles. So that would just mean that I would require 3 moles of H2 to react with 1 mole of N2, and that would produce 2 moles of NH3. So essentially what we're saying here is that the coefficients in the balanced equation can be interpreted in terms of particles or in terms of moles, right? Both of those things will be proportional because when you have a mole, right, it always equals the same number of particles. So once we understand that little piece of information, we can build something called a mole ratio. And I have a problem here. It looks a lot like the mole problems that we had done in the past. Right? We have something we can identify as a given, and then something we are asked to find or wanted. But what's different here is we're talking about 2 different substances. Right, so we're going to be building a conversion factor, but it's going to come from the information in this balanced equation. So just like whenever I solved a regular mole problem, I would always start by writing down my given, 7.25 moles, and I'm going to include the substance, the NH3 here, because when I am doing this conversion, I want to get rid of moles of NH3. And I want to convert it to moles of H2. And the way these two are related is based on these coefficients in the balanced equation. So in front of H2 I see a 3, and in front of NH3 there's a 2, so I put that into my ratio, right? That's saying that I need 3 moles of hydrogen for every 2 moles of NH3 that I get, but I've built a little conversion factor there that cancels out moles of NH3 and leaves me with moles of H2, which is what I want. And then I just have to put this into my calculator. 7.25 times 3 divided by 2. And then rounded to 3 sig figs, that equals 10.9 moles of H2. Okay, so what we did right there is the one new thing. That thing that we just made is called the mole ratio. And usually when we make a ratio like this in as a conversion factor, the 2 things in the numerator and denominator are like literally equivalent to one another. Right? If I had 1 mole of water, that would have a mass of 18.02 grams, and 18.02 grams of water is equal to 1 mole of water. They're actually equivalent to each other. In this case, these things aren't actually, like, they're different substances, so they can't be perfectly equivalent, but they are related through the balanced equation, and so we describe them as stoichiometrically equivalent amounts. Stoichiometrically equivalent. Okay. So let's see if we can build another mole ratio. It's the same equation, right? Again, we have a quantity that we're given, and this time we want to find out about moles of nitrogen. So we can tie any two substances together using a mole ratio. They can be a reactant and a product, two reactants, two products, whatever you need. Okay? But just like before, write the given. Moles of H2, right? And now I'm going to make my mole ratio. Go ahead and pause here and try it on your own before I do it. All right, so is this what you wrote? Since moles of H2 needs to cancel, I'll put moles of H2 in the denominator, and the thing that I want, moles of N2 in the numerator, and then fill in my coefficients from the balanced equation. So there's no coefficient in front of N2, so I understand that to be 1, and in front of H2 is 3. And that cancels out, moles of H2, and all I have to do is divide 12.5 by 3, get my answer, 4.17 moles of N2. Okay, a little tip when you're doing these problems, don't just write 1 mole and 3 mole, write the formula of the thing involved, because you can get yourself a little bit confused if you're only writing down numbers. So include the number, the unit, and the formula. Okay, so the mole ratio is really helpful, but in terms of practicality, we have to take this a step further. Because when we go back into the lab and we want to do a chemical reaction, we don't have balances that measure in moles. So something that would be more practical is grams. And we have the power to convert moles to grams. We did a lot of that in our last unit. So let's see if we can do this problem where this time we are starting with grams of hydrogen and we want to go to grams of nitrogen. So similar to what we did last time, but first we're going to have to convert our grams to moles before we can use the mole ratio. And then once we get our moles of our wanted, we'll convert that to grams. So our step 1 is to go from grams of hydrogen to moles of hydrogen. And we've done this a lot. So start with my given 10.0 grams of H2, convert it to moles. 1 mole of H2 has a mass of 2.02 grams. That's just 2 times what's on the periodic table, and that gives me 4.95 moles of H2. Step 2, now that I have moles of H2, I can use that mole ratio to turn it into moles of N2. So starting with my 4.95 moles of H2, I'm going to make my mole ratio. So it's 3 moles H2 in the denominator for every 1 mole N2 in the numerator. That gives me 1.65 moles of N2. And then finally, right, now that I have moles of N2, I can convert that to grams of N2. So 1.65 moles N2, and then 1 mole of N2 has a molar mass of 28.02 grams. 2 times what's on the periodic table, and that brings me to my final answer, 46.2 grams of N2. And that's a little bit more practical to work with, right? I can measure out a mass of nitrogen. Well, it's a gas, but so a little tricky, but it can still be done. Now look at what we've just done. Every single time I took an answer and made that my starting point. And then I took the second answer and made that a starting point for my third calculation. One of the selling points of dimensional analysis is that you don't have to stop and get interim answers. Instead, you can just link your factors together. Right? So this, with linked factors, would look like this. I'd still start with my given, my 10.0 grams of H2, and then convert that to moles. 1 mole of, H2 is 2.02 grams. Cancels out grams of H2. Then the mole ratio can go right in. 1 mole of N2 for every 3 moles of H2. Cancels out moles of H2. And then finally, 1 mole N2 is 28.02 grams of N2. And that still gets us to our answer, 46.2 grams of nitrogen, but with a lot less writing. Oops, I forgot to cancel out my moles of nitrogen. Right, so this is a pattern that we follow a lot, so we can kind of summarize it in a map, and I'll do that on the next slide. So since we're going from the mass of a given to the mass of a product, we're calling this the mass-mass pathway, and it's, like I said, very predictable. You'll be given grams to start with. Step 1 will be to convert that to moles. Step 2 will be to convert the moles of the thing that you're given to the moles of your wanted, and then you can convert the moles of the thing you want to grams. Now, 3 arrows there, we're going to need 3 conversion factors. So grams to moles, I'm just going to be using our knowledge from last unit, 1 mole over the molar mass for the first step, and for the third step, the molar mass over 1 mole. So that's the stuff that we've already done a lot of. And then that middle step, when we're going from moles of given to moles of wanted, that's when we do our mole ratio. And that looks like this. It always has moles of wanted in the numerator and the moles of given in the denominator. And where those little dots are, right, that's where we put the coefficients from the balanced equation. Now, sometimes when people start doing this right away, they want to put those coefficients all over the place, but the only place you do it is in the mole ratio. When you're converting grams to moles or moles to grams, it's always 1 mole and the mass of 1 mole. Don't worry about the coefficients, only plug the coefficients into that middle step. So let's practice this on another problem. Here's our problem. Right, how many grams of water are produced by the combustion of 20 grams of methane? And so we need the balanced equation. There it is. So we're starting with 20.0 grams of methane, and we're asking how many grams of water. So methane's our given, water's our wanted. Okay, and here we go. First thing, convert grams of given to moles of given. So 20.0 grams of methane, and 1 mole of methane has a molar mass of 16.05 grams from the periodic table. Cancels out grams of methane. Now that I have moles of my given, I can convert it to moles of wanted using my mole ratio. So, right, moles of given have to go in the bottom, moles CH4, and moles of what I want, moles H2O in the numerator. And then we consult the balanced equation. 2 in front of H2O and 1 in front of methane. That cancels out moles of methane. And then finally, now that I have moles of water, I can convert that to grams. So I will write in the denominator 1 mole H2O, and then the molar mass of H2O is 18.02 grams. That cancels out moles of water. And then into my calculator, I just put 20.0, and I multiply by 1, but I can skip that because it's not going to change anything, divided by 16.05 times 2. divided by 1 times 18.02 and get my answer. Rounded for sig figs, 44.9 grams of water. Pretty sweet. One more. Take a pause here and give this a shot before I do it for you here. Okay, did you get 6.81 grams of oxygen? Because if you did, you are correct. Right, so this time, our given is aluminum, 7.65 grams, and we're asking how many grams of oxygen. Okay, so here's my map, starting with 7.5 grams of aluminum. Oh, sorry, 7.65. Let me erase that. 7.65 grams of aluminum. Step 1, convert it to moles. 1 mole aluminum, and aluminum has a molar mass of 26.98 grams. And then I go to my balanced equation. I need moles of aluminum to cancel, and I want to go to moles of O2. And so it is 3 moles of O2 for every 4 moles of aluminum. 3 in front of O2, 4 in front of aluminum. Cancels moles of aluminum. And then finally convert moles of aluminum to grams. Sorry about that, moles of oxygen. 1 mole of O2, and the molar mass of O2 is 32.00 grams. 2 times 16.00, and that equals 6.81 grams of O2. Right. Pretty straightforward, pretty sweet. Just follow that map. Here's a question for you. What's a chemist's favorite plant? Stoichiometry. Ba-dum-bum. All right, now think about this. I have a question here. It looks a lot like the other ones that we've been doing, but the difference is the units that are involved. This question says, what is the mass of aluminum needed to yield or to produce 5 moles of aluminum oxide? So in this situation, we're not going from mass to mass. We are given moles to start with, and so there's no need for us to convert to moles. So we're only going to be using a portion of our mass-mass pathway. We don't need the first conversion because we were given moles to start with. So we'll see some questions like this on our homework, and you just have to carefully look at the units and decide where you're starting and where you're ending. Okay, so in this case, I'm only going to need 2 conversion factors, starting with my given, 5.0 moles of Al2O3, and I have moles of Al2O3, so I can convert that using the mole ratio to aluminum. So that is 4 moles of aluminum I wanted in the numerator for every 2 moles Al2O3 in my denominator. That cancels out moles of Al2O3, and then I can do one more step. I can use my molar mass of aluminum to convert my moles of aluminum to grams. So 1 mole of aluminum in the denominator, and the molar mass of aluminum is 26.98 grams. Cancels out moles of aluminum, and those 2 steps get me from moles to grams. On this one, my calculator gives the answer 269.8. And I can only have, 2 sig figs. So I'm going to keep the 2 and the 6. The 6 is followed by a 9, so I have to round that up, And I write down 27. But I can't stop there because 27 and 269 are not the same magnitude. And so in a case like this, don't forget to put in that place holding 0. Trailing zeros that come before the decimal don't count as significant. And that then is my answer, 270 grams of aluminum. Okay, last one for you to try. Pause it, see what you get, and then check back in. All right, did you get 1.10 moles of aluminum? That's the answer. Right, so in this case, we're starting with grams of aluminum oxide, and we're going to moles. And so once we get to moles of our wanted, we can stop. We don't have to do that portion of the pathway. So quickly, 75.0 grams Al2O3. Step 1, convert it to moles. 1 mole Al2O3 has a molar mass of 101.96 grams. Canceled out grams of Al2O3. And now that I have moles, I can jump into my mole ratio. So it is 3 moles O2 for every 2 moles Al2O3. Cancel out moles of Al2O3, and we get 1.10 moles of O2. Okay, so those are the basics. I think you should have everything you need to do your homework. So make sure to give that a try and then check your answers, and I will see you in class.